So, if we consider probability that A is the last person to throw a 6, that will be equal to 1 minus 5 by 6 to the power r 2 times. So, it is a square of this, and then we consider the probability that A has no 6 up to the rth trial, its rth trial, and the 1 by 6 on the r plus first trial. So, that is 5 by 6 to the power r into 1 by 6. So, here we will get 3 infinite geometric sums, and if we add after simplification, it turns out to be 305 by 1001. Once again you can see that this is less than the probability that A is the first to throw a 6. Let us look at some applications of the conditional probability now. Consider all families with 2 children and assume that boys and girls are equally likely. If a family is chosen at random and is found to have a boy, what is the probability that other one is also a boy? This is one part of the problem. In the second part, we ask, if a child is chosen at random from these families and is found to be a boy, what is the probability that the other child in that family is also a boy? Notice here that the sampling scheme is different. In the first one, the family is chosen, in the second one, the child is chosen. You will see that representation of the sample space will be different in these both cases. Let us take the first case. In the first case, we are considering families with 2 children. So, we can put it as an ordered pair, both of them are boys, first is a boy, second is a girl, first is a girl, second is a boy, or both are girls. So, A is the event that the family is a boy, then probability of A will be 3 by 4, because out of this possibilities, if you see, because we are choosing a family. So, family means it could be this, this, this or this, and therefore, one boy is appearing in 3 places, at least one boy. So, the family has a boy, probability of that will be 3 by 4. So, now if I define the event that B, that second child is also a boy, then conditional probability of A given B is probability of A intersection B divided by probability of A. So, probability of A intersection B corresponds to the possibility that both the children are boys. So, this is only one possibility, and therefore, the probability of that is 1 by 4. So, if I take the ratio of probability of A intersection B with probability of A, we get probability of B given A as 1 by 3. That means, if in a randomly chosen family, if a child is found to have a boy, then the probability that the other one is also a boy is 1 by 3. Let us look at the second part of this problem. Here the sampling scheme is different. So, here from the collection of all the families, we choose a child at random. If a child is chosen at random from these families, so that means the child can be a boy with a brother, the child can be a boy with a sister, the child can be a girl with a boy, the child can be a girl with a sister. So, here you can see the representation of the sample space is different, although here you may feel that we have written it in this way, boy, 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 girl, etcetera. So, it can be also considered as a brother or sister relationship. However, it is not so, because here we are choosing randomly the family, whereas here we are choosing a child. So, the child may have a boy, may have a brother or sister. So, the representation of the sample space is quite different. So, what is the probability that the child is a boy? It will be simply half, because it could be a boy or it could be a girl, both are having 2 possibilities. B, the child has a brother. So, if I look at probability of A intersection B, it means the child is a boy and it has a brother. So, it is this possibility, that is 1 by 4. So, probability of B given A becomes half. Notice here, the answer in the beginning may look to be the same, that if a family is chosen at random and is found to have a boy, what is the probability that other one is also a boy? We are getting the answer as 1 by 3. Whereas, in the second case, the child is chosen, what is the probability that the other child in the family is also a boy? Here it is half. So, it may look counterintuitive, but it is because the answers are coming different, whereas the event looks to be the same. However, it is not so, because the sampling scheme is different in both the cases, and therefore, the representation of the sample space itself is different in both the cases. In the first case, the sample space is described like this, and in the second case, it is described like this. Let us look at some further applications of the conditional probability. So, consider a example. There are two kinds of tubes in an electronic gadget. It will cease to function if and only if one of each kind is defective. So, there are two kinds of tubes. So, if both kind of tubes, so at least one of each kind is defective, then the gadget will fail. The probability that there is a defective tube of the first kind is 0.1 and the probability that there is a defective tube of the second kind is 0.2. It is known that the two tubes are defective. Now, these two tubes could be any combination, both could be first kind, both could be second kind, one could be first kind defective, second kind defective, etc. So, what is the probability that the gadget is still working? So, let us define the event A, that the two tubes are defective, and B is the event that the gadget still works. That means, we are interested in finding out the conditional probability that B given A. So, we need to look at the probability of A intersection B and probability of A. So, probability of A, that the two tubes are defective. So, here we can have 4 different possibilities, and here we will make use of the independence of the individual tubes to be working. That means, we assume that each tube fails or works independently of the other tubes. So, if both the tubes are defective of the first kind, then the probability will be 0.1 into 0.1, that means 0.1 square. Both may be having defects of the second kind. So, it is 0.2 into 0.2, that is 0.2 square, or first one could have defect of the first kind and the second one could have defect of the second kind, or vice versa. So, it will be 2 into 0.1 into 0.2. So, this is equal to 0.09. Now, what is probability of A intersection B? A intersection B is the event that the gadget is still working and the two tubes are defective. That means, it ensures that we can't have one tube to be defective of one kind and another tube to be defective of another kind, because in that case the gadget will not be working. Therefore, both defects are either of the first kind or both are of the second kind. So, here we have made use of that probability of union is equal to sum of the probabilities of disjoint events, and we have made use of the concept of the independence. So, if we add this after simplification, this turns out to be 0.05, and therefore, the conditional probability of B given A is equal to 5 by 9. We consider some further applications of the conditional probability. Here, we will like to show one interesting phenomena, that is the probability of repetition of certain event increases. Let me explain through the example. So, a machine has certain screws fitted. So, all the screws in a machine come from the same factory, but it is as likely to be from factory A as from factory B. That means, either all of the screws have been selected from factory A, that means probability is half, or all of them are taken from the factory B, the probability is again half. Now, in both the factories, some of the screws may be defective. So, the percentage of defective screws is 5% from factory A and 1% from factory B. So, two screws are inspected one by one. If the first screw is found to be good, what is the probability that the second is also good? I am looking it in the reverse way also. If the first screw which is inspected is found to be defective, what is the probability that the second is also defective? In order to evaluate this, let us define the events. let G1 denote the event that the first inspected screw is good. Then what is the probability of G1? Then probability of G1 is actually by using the theorem of total probability, that all the screws came from A into probability of A plus probability of G1 given B into probability of B. Now, probability of A and probability of B is half. What is the probability of good screw coming from factory A? So, since 5% of the product coming from factory A is defective. So, the probability that a good screw is there from factory A is 95 by 100. In a similar way, probability that the screw is good coming that it is from factory B, it will be 99 by 100, because 1% of the factory B products are defective. So, after simplification it turns out to be 0.97. Now, we look at the event that the second screw is also good, that is the one after another the screws are inspected. So, first screw has been found to be good, what is the probability that the second is also good? So, we look at the event G1 intersection G2. So, first screw is good and second screw is good. Once again, if we represent this event, it becomes probability of G1 intersection G2 given A into probability of A plus probability of G1 intersection G2 given B into probability of B. So, here probability of A and probability of B both are half. Here first screw is good, that is with probability 95 by 100. Now, all the screws are coming independently from the factory A or factory B. So, at each inspection the probability of them being defective or good remains the same. So, it will be 95 by 100 into 95 by 100 if it is coming from factory A. In a similar way, if we are looking at from factory B, it will be 99 by 100 into 99 by 100. So, after some simplification, probability of G2 given G1, that is probability of G1 intersection G2 divided by probability of G1. So, after simplification it turns out to be 0.9704, which is clearly bigger than 0.97, that is the probability of G1. So, the comment that I made in the beginning, that the probability of some repetition of certain event increases. So, we are saying that if a screw is good, then the second one is also good, is probability is higher. That means if it is found to be good, that means the supplier who has given, we are taking from the good ones, and therefore, the second trial will have a higher probability of being good. So, probability of G2 given G1 becomes 0.9704. Let us look at it in the reverse way. Consider D1 to be the event that the first inspected screw is defective. So, probability of D1 using the argument which we considered earlier. So, we can write it as probability of D1 given A into probability of A plus probability of D2 given D1 given B into probability of B. So, this is equal to half the 5% from supplier factory A are defective, that is 5 by 100, and 1% from the supplier B are defective. So, it is 1 by 100. So, it is 0.03. So, if I look at the event D2, that the second screw is also defective, then once again we can use the same representation. This is equal to probability of D1 intersection D2 given A into probability of A plus probability of D1 intersection D2 given B into probability of B. So, by the logic which we used earlier, it is half into 5 by 100 square plus 1 by 100 square, that is 13 by 100 square. So, if I look at probability of D2 given D1, that is probability of D1 intersection D2 divided by probability of D1. So, which after some simplification becomes 13 by 300, which is clearly bigger than 3 by 100. Once again you can see that this probability has increased. What does it mean? It means that if the first one is a defective, it means that there is more likelihood that the supplier which is giving more defectives is the one which has actually given, and therefore, the probability will increase that for the second one also to be defective. In fact, we can consider a more general problem here, where we can replace these numbers by some abstract expressions, some numbers between 0 and 1, and similarly this probability of selection from each one, in place of half we can put some alpha and see that this phenomena still holds. So, let us consider this problem. In any given year, a male automobile policy holder will make a claim with probability P m, and a female automobile policy holder will make a claim with probability P f. In general, we assume P m is not equal to P f, although it is not necessary, it may be equal also. The fraction of policy holders that are male is alpha, where alpha is a number between 0 and 1. A policy holder is randomly chosen, and A I denotes the probability that this policy holder will make a claim in the year I, for I is equal to 1 to. What is probability of A 1? What is probability of A 2 given A 1? In general, show that probability of A 2 given A 1 is greater than probability of A 1. So, once again it is a question of repetition. That means, if the person has made a claim in 1 year, then in the second year he will again make a claim, the probability increases. Basically, it means that if he has made a claim, that means he is more accident prone person, and therefore, it is more likely that in the next year also he will make a claim. If you look at the practical application of this, suppose you purchase a car and you take an insurance. So, you will have to pay a certain amount, say P. Now, if you did not have any accident during the year, your premium gets reduced to some number P star less than P. If you in the second year again you do not have any accident, your premium will be further reduced in the next year, and it will keep on reducing in the subsequent years. Even if you purchase a new vehicle after say 5 years, and the usual premium on the new vehicle is say Q, you will be asked to pay only Q star, which is less than Q, based on your past performance. However, if you commit an accident, then and you make a claim, then your premium will become much more. So, this phenomena, that is the probability of the repeat event becoming more, is used in practice by the insurance companies. So, let me give the solution to this problem. So, using the same argument, that probability of A 1, that means the person makes a claim. It is by using the theorem of total probability. This is probability of A 1 given that he is a male, plus probability of he makes a claim given that he is a female, the person is a female. So, the probability of a male is alpha and probability of female is 1 minus alpha, and probability of making claim for male is P m and probability of a female making the claim is P f. So, it is alpha P m plus 1 minus alpha P f. By using the same argument, probability of A 1 intersection A 2 becomes alpha P m square plus 1 minus alpha P f square, and therefore, the conditional probability that A 2 given A 1 is equal to probability of A 2 intersection A 1 given divided by probability of A 1 is this. Now, this conditional probability is greater than probability of A 1. You can actually write this expression and simplify, it is reducing to alpha into 1 minus alpha P m minus P f whole square. So, unless P m is equal to P f, this term is strictly greater than 0. So, in the unlikely case where P m is equal to P f, then this will be equal to 0, that means the two probabilities will be same. However, P m is equal to P f simply denotes that it does not make a difference that where from you are choosing. That means, both have the same probabilities of say either defective or non-defective or making a claim or not making a claim. So, in that case the phenomena will not change the probability, because here the effect is coming because if we are saying that the person makes a claim. So, that means he is more accident prone. So, that is why he should have a higher probability in the next year. Consider a communication channel. So, here again it is some further applications of the conditional probabilities. So, we have a trinary communication channel. So, let me explain these things. So, T I means that digit I is transmitted. So, T 1 means that the digit 1 is transmitted, T 2 means digit 2 is transmitted, T 3 means digit 3 is transmitted, R 1 means digit 1 is received, R 2 means the digit 2 is received, R 3 means digit 3 is received. So, it is a trinary communication channel. Now, digits 1, 2, 3 are transmitted, however, due to noise in the channel they may not be received as the same. So, probability that a 1 is received given that it was sent is 1 minus alpha, whereas probability that it is received as 2, that is probability of R 2 given T 1 is alpha by 2, probability of R 3 given T 1 is alpha 2, that means alpha by 2, that means 3 is received given that 1 is sent is alpha by 2. That means, with probability 1 minus alpha it is correctly sent, and with probability alpha by 2 each it is going as some wrong numbers. It is due to the noise in the channel. Likewise, probability that a 2 is received given that a 2 was sent is 1 minus beta, and it is beta by 2 for the other two possibilities. And similarly, probability that a 3 is received given that a 3 is sent is 1 minus gamma, and gamma by 2 each is the probability that it is received as 1 or 2. Further, we assume that in this communication channel 3 is transmitted 3 times more frequently as a 1 and 2 is transmitted twice as often as 1. If a 1 has been received, what is the probability that 1 was sent? What is the probability that a transmission error has occurred? What is the probability that a digit I is received for I is equal to 1, 2, 3? So, let us look at the probabilities of each of these. So, firstly we look at the conditions of the problem. 3 is transmitted 3 times more frequently than 1, 2 is transmitted 2 times as frequently as 1. Therefore, the probabilities of 1 being transmitted, 2 being transmitted and 3 being transmitted are as follows: 1 by 6, 1 by 3 and 1 by 2. Further, it is given that the conditional probabilities of R 1 given T 1, R 1 given T 2, R 1 given T 3, R 2 given T 1 and so on. Now, if we look at probability of T 1 given R 1, that means the digit 1 is received, what is the probability that 1 was sent? So, it is a direct application of Bayes theorem, because T 1 is a priori event, because the digit is sent before and it is received afterwards. Now, in the light of the new information that what has happened afterwards, what is the probability of a prior event? This is what we call posterior probabilities, and we will use Bayes theorem here. So, probability of T 1 given R 1 is equal to probability of R 1 given T 1 into probability of T 1 divided by sigma probability of R 1 given T I probability of T I is equal to 1 to 3. So, all the expressions are given here and we see substitute. So, after simplification it turns out to be twice 1 minus alpha divided by twice 1 minus alpha plus twice beta plus 3 times gamma. In fact, in a similar way we can calculate probability of T 1 given R 2, T 2 given R 1, T 2 given R 3 and so on. What is the probability of a transmission error? Now, transmission error is the post event, that means, firstly something is sent, something is transmitted, therefore, it is conditional upon what was actually sent. So, there are 3 possibilities of sending the digits 1, 2 or 3. So, again by using theorem of total probability, probability of transmission error becomes transmission error given T I into probability of T I. So, what is the probability of T1, that is 1 by 6, and what is the transmission error, probability of transmission error given that 1 was sent. It is alpha, because 1 minus alpha of correctly sending. So, it becomes alpha into 1 by 6. In a similar way, if the digit 2 is sent, then with probability beta it is not received correctly, with probability 1 minus beta it is received correctly, and with probability 1 by 3 the digit 2 is sent. So, the probability becomes beta by 3. In a similar way, the probability of transmission error, if 3 is sent, is gamma, and half is the probability of sending the digit 3. So, the probability is evaluated here. What is the probability that digit 1 is received? What is the probability that the digit 2 is received? What is the probability that the digit 3 is received? In each of these cases, the digit getting received is a consequence of digit being sent. So, at each stage the theorem of total probability is applicable, and the expressions for the conditional probabilities are given here. We can utilize them to get the expressions for that the digit 1 is received, or the digit 2 is received, or the digit 3 is received. Let us look at some more applications of the conditional probabilities. 4 firms A, B, C and D, they are bidding for a certain contract. A survey of the past bidding success of these firms on similar contracts shows that the following probabilities of winning the contract are, that is, A will win the contract with probability 0.35, B will win the contract with probability 0.15, C will win the contract with probability 0.3, and D will win the contract with 0.2. Before the decision is made to award the contract, firm B withdraws its bid. Find the new probabilities of winning the bid for A, C and D. So, basically what does it mean? It means that if B has withdrawn, that means B cannot win the bid. Therefore, probability of A winning is actually now the conditional probability of A given B complement. So, by using the definition of the conditional probability, it becomes probability of A intersection B complement divided by probability of B complement. Now, here you notice that B complement means that B does not win the bid. Therefore, A winning the bid is actually a subset of this. Therefore, A intersection B complement is simply probability of A. So, if we substitute the probabilities here, we get it as 7 by 17. So, in a similar way, probability of C given B complement turns out to be 6 by 17, and probability of D given B complement turns out to be 0.2 divided by 0.85, that is 4 by 17. So, if B has withdrawn, actually his share of probability is allocated to the other 3 bidders here, and that is why the probabilities are getting modified. In place of 0.35, it has become slightly more than 0.35. In place of 0.3, it has become slightly more than 0.3. In place of 0.2, it has become slightly more than 0.2. Let us consider a communication channel. This is an electric network. The current flows from A to B. However, there are 3 independent paths here, which we call say E1, E2, E3. There are circuits here. So, 1 by 5 denotes that the circuit this failure of the link, this link, that is the probability of failure here. 1 by 5 is the failure of this link, 1 by 3 is the probability of failure of this link, 1 by 4 etcetera are the probability of failure of these links. What is the probability that the current is actually flowing from A to B? So, if we denote the 3 paths by E1, E2, E3, then it is probability of union of E I, which is equal to 1 minus probability of intersection E I complement. Now, here each circuit is working independently, each path is working independently, therefore, probability of intersection becomes product of the probabilities. Now, here it is 1 minus, now here probability of even complement. So, even complement means that this circuit is not working. It is not working if either of this is failing, or it is working if both are working, that means 4 by 5 square. So, it becomes 1 minus 4 by 5 square. This will not work with probability 1 by 3, this will not work with probability 1 minus 3 by 4 square. So, after simplification it becomes 379 by 400, which is pretty high. So, this is because of the redundancy in the system, because if any of the path is working, the current will be flowing from A to B. So, here in today's lecture we have given various applications of the rules of the probability. Thank you.